Acid chlorides are very versatile organic compounds, as we have seen previously. Acid chlorides can be transformed into all other carboxylic acid derivatives which are less reactive than them. For example, acid chlorides can be converted into acid anhydrides if they are reacted with a carboxylate ion. Acid chlorides can also be converted into esters and amides if they are treated with alcohols and amines respectively. Acid chlorides can also be converted into tertiary alcohols if they are reacted with a Grignard reagent, or if they are reduced with a strong reducing agent such as lithium aluminum hydride, they can be transformed into the corresponding primary alcohols. Ketones can also be made from them if acid chlorides are reacted with a Gilman type reagent or a cuprate, being a mild organometallic or mild nucleophile. Let's take the first reaction, which is conversion of an acid chloride into an acid anhydride. Let's draw the general scheme for this reaction. So this is an acid chloride. That's a general structure for an acid chloride. And this is the nucleophile that's required in this case, which is the carboxylate, if an acid anhydride is desired. So this is the general structure of an acid anhydride. So that's an acid anhydride. This reaction is likely in the way it's drawn. So as an acid chloride, when treated with a carboxylate ion, being a conjugate base of a carboxylic acid itself, it can be converted acid chloride into the corresponding acid anhydride. Now, this reaction is likely, but the opposite reaction again is not likely. As we have seen the trend, the general trend before, is that it is possible always to make a less reactive carboxylic acid derivative from a more reactive one. That's because of the nucleophilicity, of course, of the nucleophile and the leaving group ability. For example, the chloride ion, which is the leaving group in this reaction that leaves, is a better leaving group than the carboxylate ion itself. Okay, so this reaction is possible, and the opposite or the reverse would not be possible. Let's work out a mechanism for this nucleophilic acyl substitution reaction. The carboxylate ion will act as a nucleophile, so we can take an arrow from the carboxylate ion. The carboxylate ion then attacks that carbon. Of course, that carbon again is electrophilic, not only due to inductive withdrawal by oxygen, but also because of resonance withdrawal, as we have seen also in a previous lecture. So this carbon-oxygen double bond is then broken with the release of electrons on oxygen. So we can write the intermediate after this nucleophilic addition step, which is a nucleophilic addition actually, so it's addition, but then again we can continue with the elimination of the leaving group. So we can assume that the carbonyl group is reformed by drawing an arrow like that, so the other head of that arrow again, so reformation of the oxygen carbon double bond with departure of the leaving group. So addition followed by elimination. So this is nucleophilic acyl substitution reaction again. That's nucleophilic acyl substitution, an addition step or a nucleophilic addition step that is followed by elimination of the leaving group. So what we get is the product that's required, which is the acid anhydride, of course. So it's a very simple, very important, yet very important mechanism. If you recall, again, these carboxylate ions are actually made from carboxylic acids themselves by deprotonation with a suitable base, such as the hydroxide ion, for example. So that's how these carboxylate ions are made. They are made from the corresponding carboxylic acids. So again, this reaction is a very useful reaction for the transformation of acid chlorides into acid anhydrides by reacting the acid chloride with a carboxylate ion.